Okay, so for this training, we are talking about object serialization and deserialization. Okay, so we will describe what it is. It's a very important concept. Yeah, so the motivation for doing serialization, there are several reasons, right? The first reason is for space efficiency, okay? Because if you think about it, if you have a number, let's say if it 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, 10, right? If you store it as a string, even though it's a floating number, right? If you store it as a string, there will be how many bytes? Gila, how many bytes?
10 strings.
11 bytes. Okay, each is a character, including the dot. Okay, there's 11 characters. It's okay?
Okay, as a string each one. Okay.
Yeah, 11 bytes. Okay, but if you keep it as a float, it's how many bytes? Gila? Not double.
Each one is
yeah.
4, I guess.
Yeah, 4 bytes. Okay, so it's 4 versus 11. Okay, so binary stream is much compact. It's okay. So it's space efficient even for in run. Okay, yeah. All right, so this is usually binary stream. Okay, otherwise it doesn't make too much sense. Sorry. Okay, so an example that even in memory you need this is Hadoop. Okay, so I'm not sure how many of you have used Hadoop Deserialization, Hadoop MapReduce, right? So basically you are writing a mapper and you're writing a reducer, right? So in the mapper, the interface should all be writable. And what is writable, right? So writable means, you know, it can be serialized into a binary stream, okay? Like this is a data output, means a output binary stream, which can be saved to disk and sent over over the network, right? And this is data input stream, right? You can read a fields in binary stream, which means, for example, if your network send you a stream or you know, you have a file stream on disk, you will be able to read it one by one, calling this, okay? So this is called an interface in Java, which means it's a virtual function, right? So it's an abstract function without any implementation, and you need to implement this interface, right? So for example, if you have a bool, then your bool may not know how to write the bytes, right? Bool is 1 byte, by the way, right? So into a stream, right? So binary stream, okay? And you need to inherit this writable interface. And with that interface wrapper, this is called a Boolean writable, okay, integer writable. String writable is actually called text in Hadoop, okay? So these should all be writable, okay? So the reason in Hadoop is very simple, right? So you have key value pairs, you have so many, maybe 1 terabyte. You cannot put them in memory, right? So basically it's from a file stream, okay? And you have a small buffer of these key value pairs where you stream into memory, right? So this is always a binary stream, okay? And including if you later you reduce, you output some binary stream, it will be on disk, right? And on the disk, this stream will periodically be shuffled to the other machine by reading the message stream onto network and sent to the other side, right? Any questions?
It's fine.
Okay. I think I need to clean this loop. Yeah, so one reason is in memory, it will be compact. The second reason is that you want to save the object on disk, right? So the reason why it's so difficult is because, you know, so these objects, if you look at what we teach you, right? So, you know, sometimes maybe this is your main stack, right? The main function stack, but you have a vector, but this vector or this maybe map points to a binary search tree, right black tree in the heap, right? All those, and each heap, this node is actually a left pointer and right pointer, right? It's super complicated, okay? How to translate this whole data structure into a binary stream, right? So if you directly say, hey, I want to save it, it's not so simple because it's kind of pointers to different locations in the memory, okay? So you need something called a binarization, right? So the serialization, okay? So Python basically did that for you for basic types, okay? So if you have the basic types, like if you, for integer, just like a writable interface before, okay? For integers, they know how to do that, right? So then you have more complicated if you have a list of integers, right? And they tell, also, we will see how this is done in our case, using our library, okay? Basically, if every item is, you know, serializable. Okay, and the container, it also defines a function. Say, hey, how to serialize these items one by one in the container if each item is serializable, right? So then the recursively define those containers are also serializable. But some objects may not be serializable. For example, one example is a model object, right? So then you have to call maybe Keras model.save. So they will tell you how to save this thing, right? Because a lot of the internal serialization APIs are not defined there. Okay, just like those APIs, right? If you define this, then things will work out. If you don't define these, things will not work out. Okay, in Java, unfortunately, we have to wrap a writable, basically have a new class for that, right? So unfortunately, because they don't support operator overload. In C++ and in Python, they support operator overload. So a lot of basic types, they already have an operator saying how you can stream into a output stream and input stream in a binary stream. Okay, so things are fine. But maybe for your machine learning model in Keras layers, they didn't do that earlier, right? So they have their own format. Okay, then basically you have to call their function. You cannot use pickle. If you call pickle to save, it will report error because some of the loading dumping function on the binary stream is not defined there. Okay, any questions?
It's okay.
Yes, Professor, could you please remind me what an operator is?
Okay, let me see. Let me open a new window. So operator only C++ is something like this. Okay, so let me see. You can define a plus, how to plus a box with another box. Okay, and then you can later do box plus. I think somewhere here. It's okay.
Okay.
So all this is done is following this operator. So if you don't remember, you can check our training video last time.
Okay.
Okay. Yeah, this is called operator overloading. Okay, and in Python we have something like that dash add, right? So or you can call it magic function. Okay, but Java don't have this. So all you can do is wrap another class. Okay, so in Python it's the same basically, right? So you tell him how you can add b, right? So then you can call it a plus b somewhere. Okay, yeah. So basically you have a class day, and if you have 2 days added together, then you can do this. Any questions?
Thank you so much.
You're welcome. Okay. Yeah, again, so if you forgot you'd better check out our training video. Okay. All right. Yeah, unfortunately, Java cannot do that, right? So you have to wrap another class that implements this interface. Okay, so that's why Java is so. I don't really like Java. Okay, and so another important reason is that you need to send some object through the network, right, to another machine, right? And as we said, some of the data may be very complicated, right? So they have a bunch of pointers point to different locations, and maybe point to a root node of another red black tree, and each red black tree node have left child, right child, click everywhere, right? So how to stream them into a bit stream sent over to the other side, and then the other side can deserialize, right, into the object in its memory. Okay, so basically when you do this, when you serialize out and serialize in, it will be another object. It will not be the original object, but the content is exactly the same. It's okay?
Yes.
Okay. Right, so another example is in Python, we have pickle, right? So here's an example where you have the data, which is, I think, a list with only one item, which is a dictionary. And this dictionary has 3 items, right? Key A, value A, key B, value 2, etc. Okay, right. And so, Python, basically, you can have different types of values, right? So containers don't have to be the same type, okay? In the other language, like C++ and the Java, this is not acceptable, okay? And so what you do is, for example, before, so you create this list object, right? So, and you print it. So you print before, this is like this. And then you kind of pickle it, right? So, because each floating number string, they know how to pickle, right? And then the dictionary is also defined how to pickle if every key value serializable. Okay, and then a list, right? If your item in the list is serializable, the list will become serializable. Okay, we will see how this is done in our using our library. Okay, not in Python. Okay, in Python, something similar basically. Okay. And now after you save this to data1, which could be save this data1 to something some this string, right? Then this becomes a binary string, right? Then you can load it back. Okay, when you load it back, then into another object data2, right? And then you print data2. Okay, so that now you have 2 copies of the object, right? But this string will be binary string, which will be very tight. Okay, so and then you can print it. So this is data2, this is data1. Okay, and now you can see whether data1 is data2, right? This will be false because it's 2 copies, right? If you compare them, basically it's in Python, it's like a pointer in C++, right? You check whether the starting pointer of these data blocks are the same, right? The address is not the same, okay? But the next you have the equal, right? The equal is more like a overloaded operator, right? So whether the content are the same, then this will be true, okay? I think maybe
Yes.
Sami will ask this, right? So let me see. How can I open the browser here?
Sorry, sir.
Yeah, so
You,
operator equal. You can also do this. It's okay?
yes, sir. I knew that about Python. The difference between is and equals.
Okay, yeah. So there are different operator. You can overload equal. Okay.
Mhm.
Right. So there are 2 different you can operator. Let me see. Equal and symbol you can operate. Okay, but there are also a copy constructor. So there are 2 different things. Okay, if you initialize using equal, it's using copy constructor. Okay, so for example, if you are doing something like this, right? So let's say you have A, you have a copy construct B, right? So this is using copy constructor. Okay, it's not calling the operator overload equal. And this is even the case if you are doing this. Okay, so A equal to B, right? But if you do something like A first, right? So and then later you say A equal to B. This is this is assignment constructor, right? So now we are talking about the this operator. So basically, what I want to say is in C++, this will be calling the copy constructor. Okay, this will be calling the operator assignment overload. This will be equal overload. Okay, so here equal overload is overloading. So we have data item 1, right? So this is data 1. Okay, which is something like this, and then we serialize into a string object, right? And this string object put in here and serialize into exactly the same content in data object 2. Okay, but their pointer, if you use is operator, the pointer, the address is different. Okay, right? All the other language are hiding pointers, but it's stupid. Okay, so if you don't know the pointer, you don't really have any deep understanding. Okay, their address different. This equal is using the operator overloading. Okay, so you are comparing each byte whether they are the same. Okay, then this is true. Any questions here?
No, thank you.
Yeah. All right, so next is, for example, in Java, we also have serialization, right? So there's a serializable interface, right? And all you need to do is serializable because they know how to serialize string, int. If you don't want to serialize something, you do transit, right? So the transit is variable modified in serialization, right? You don't want to save the value, okay, into the string, right? When it load back, it will only load these 3 values, right? This will be something like initial value, like 0 or undefined. Okay, I think in Java it will initialize to 0. In C++ it will be undefined. Okay, so next is so once you define something to be serializable, how you can do that, right? So how to use it, right? So for example, this employee previously was defined as a serializable object, right? So if you go back to the previous page, right? So this employee is serializable, okay? And now for this employee, you can just using the so-called you say a file, and this file is thrown into an object upstream. Then you can write an object and read an object. Okay, so because they are serializable. Okay, and here is example where you can read an object. Let me clear this. So you can, let me see. Then you can have an in file stream throw to here, and then you can read it. Right. So and you can read it one by one. Okay. Any questions? So this is
That's okay.
Java. Okay, yeah. So in Hadoop, they say that hey, Java, this kind of serialization is very efficient because they save all the class information. If you look at their serialized object, it's very it's not a space efficient. Okay, it's unlike byte stream in Python or in C. Okay, so that's why they have the C pickle, right? So you can use pickle. You can also overload the C pickle to be pickle. Okay, C pickle is a C implementation of pickle, which is way faster. So you don't. I don't think there's any downside on using C pickle. It's exactly the same as pickle, but it's faster. Okay. Right. But Java is very, very bad design. So I always feel very headache about Java. Right. So Hadoop has their own serializable interface. Right. So you just saw that. Okay. So the read field, right? So the one that we see earlier. Let me see what. This one, okay? So these two functions, right? They define their own serializable because Java's native serializable interface is a disaster, okay? And yeah, so you can see the read field. And so this is another API called, if some of you have gone to the tutorial that we discussed, right? So about think like a vertex, like, so you have vertex objects, you can send a message to each other, you can have edges, right? So this is a vertex ID, this is a vertex value, this is edge, this is message, right? Logically, you only need the messengers, right? Only messengers are passed along the network, right? So this should be writable interface, right? But unfortunately, all of them should be writable. By the way, the ID should be comparable, right? So you can overload the smaller than equal to smaller operator, right? In some sense, in Java, it's a comparable interface, okay? So that you can solve the vertex, etc. Others are just writable, okay? You can write to the stream, just like in Hadoop, okay? Why besides messages, we also require the ID of vertex value, vertex edge, also to be serializable, right? So the reason is actually people find, hey, Java is just a disaster. Okay, so they don't have delete, right? So in Python we have del an object, right? The object is removed from the memory. Otherwise, it will always be memory. In C++, we have delete, right? And delete array, etc. Okay, Java just get away of this, right? This is not a good option actually because you can never delete something, right? It's the garbage collector GC is doing that, and the GC is doing a very bad job, and it's an independent thread. So when you use up your memory, it will be running forever, but there's no way to cleanly remove all the content. Okay, it's a disaster in some sense. Okay, and so there are people talk about bloat-aware design for big data applications, and it's basically saying in this Prego-like system, think like a vertex-like system, right? So they need to make everything writable, okay? So that in memory, so it's a byte stream. What you can do is you can save these things, right? So as binary streams. So in that case, it becomes a byte array, which is one object, okay? With starting and end locations, right? So that's more manageable, right? So it's one object. If you make them many objects, right, like these, then the garbage collector will get crazy, right? So when I should delete this, when I should delete this, basically Java will, basically there's no performance. It's okay?
Yes.
Yeah, so originally Giraffe is doing all in memory, so it's not good, and they propose this. I think Giraffe also improved, makes these three also serializable. So I think really we should not use Java to develop big data systems. Okay, the only thing why Hadoop is fine is very simple, right? So when you have a mapper, right? So you are reading from a file to get key value pairs. Okay, key value, key value, key value. So you can have a streaming, a small buffer, right? And then when you send you emit things, right? These will write another to disk, and these will go through network, right? And the reducer side, it will get this stream into key value pairs and emit new key value pair to a file. Okay, Hadoop digital file system. Everything is on disk. Okay, but when you want to keep those objects in memory for computing, right? So like a graph, then things get crazy. Okay, so actually it's not exposed. The problem is not posed when they implement Java version of Hadoop, but when you implement in-memory computing model, things just crash. Okay. And in C++, because Jalal will mainly be programming C++, right? Do we have serialization? Yes, there's a Boost library. Basically, Boost library go ahead of C++ standard, right? So they have all kinds of new containers and serialization and even MPI wrapper. Okay, so that are not yet standardized into C++ maybe 11, 17, 28, right? So but these things could be useful. So then they have a lot of library to do that, right? So I don't really go to Boost because I don't feel the need. Okay, so because a lot of so when you use Boost, you need to install it. Okay, and so in a lot of the servers, you don't have the right to install things, right? So then you need to talk to the administrator. Okay, but Boost itself is really a good library. Okay, but it's heavy, which means if you just want to include a small serialization module, it's dependent on a lot of other things, right? The compilation speed will be very slow. Originally, compile file, maybe your code is 2 seconds. Now using Boost, maybe 10 seconds, right? So you need to wait for longer, okay? If you have a big system. All right, so next will be, we will talk about our own library, right? So that Jalal will need to understand everything here, okay? One is called serialization, which is serialization to in-memory buffer. Is okay?
Yes.
Another is IO serialization, which means it's serialization to the disk. Is okay?
Yes.
And they are all in gsyncer, right? So the links are here. I will send, if I forget to send this slide, just remind me, okay?
Yeah, sure.
And compared with Boost, we have no installation and fast to compile. And we understand everything down there, right? And it's just the header files, include and use, okay? It's much easier, right?
Yeah.
So the first is the in-memory binary stream, right? Serialization.h, and it's used for buffering messages and objects, right? So to send to remote machine, because when you have a bunch of, let's say you want to send a message, right? So you're sending message object into buffer, right? But buffer will buffer for a while and then send in one batch periodically into the other machine. Okay, because there's some startup cost, right? You have header, etc. Right? So if you send each item to the machine and then another item again, this is slow. Okay.
Yes.
You want to batch them to send, right? So like a frame, etc. Okay. So in order to do that, we need to make this a binary stream, right? And they can cut and send. Okay. For that reason, actually the buffer will be streaming these objects. Okay. So that's why we need a in-memory byte stream that we can send over the network. Yeah, keep in mind. So we when we do the programming, we have objects in memory, right? So, but when we send, we want a byte stream to send. Okay, so this is one purpose we are doing this, but actually it has a lot of other use. Okay, so not just this, right? So this is just one purpose of that, right? So let's take a look at how this is implemented, right? So this is more like this class is similar to C in C out in C++, okay? Or if in if stream. Is it okay?
Okay.
The only difference is that everything is in binary form. Okay, like C in C out is in text form because it's operating with humans, right? C in C out is a text string. It's okay.
Yeah.
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 Okay. Just one moment. Let me check if there's any important thing. I think. Okay, because I'm getting emails. Yeah. So what we do internally is a byte array. It's okay? Yeah, it's a byte stream. It's a byte array. It's okay?
Okay.
Yeah, so it's just a wrapper of byte array with a bunch of operations, how to manipulate on the byte array. Okay?
Okay.
Char is byte. It's okay? In C++.
Okay. Yeah.
Yeah, and you can pen, right? You can push back in C++. We call it pushback. Okay?
Yes.
So then you can insert if you have more than one character. Okay, so that's just appending things to the byte array. That's the binary stream for writing. It's okay.
Yeah.
Yeah. Okay. And so one important thing is that we let's say if we finally have this byte stream, right? So we want to send things out, right? So we need to take the beginning header location of the buffer and also how many bytes, right? Then we can send out to the MPI, for example. Is okay?
Yes.
Yeah, for this reason, we need to get this pointer, right? So this pointer is by this function, okay?
Yes.
Yeah, put simply, if you don't remember how this functions, let me briefly describe. So basically, this buffer is a vector, right? So buffers brackets is operator overloaded. Okay, so this is a vector. It has an internal character pointer in the heap, right? An array A is okay, right?
Yeah, yeah, yeah.
But when you call the bracket, it will get actually internally it's called A0. It's okay. Right, so this
Yes.
item, and then you get its address. So this is the address pointer to this location. Okay, right.
Yeah, yeah.
Then you get this internal buffer, and you can send out. Right. So this is to get the buffer of this vector. Okay.
Yes.
Okay. Yeah. So you can also get the size. Right. It's just a vector. How many bytes? Right. So you can clear the buffer. You can push back. For example, if you just append a character, you just call the raw byte to push back byte.
Yeah,
Right?
yeah.
If you
And the
append
last one will push a size.
yeah, if you push back a bunch of characters, maybe 8 characters, right? So you say 8, and this is the first
Yeah.
character address, okay? Put here. It will we call insert function to do that. It's okay?
Yes.
Yeah. The reason we make it void because it's not always a character. Okay, it may be integer or float, double, right? Double is 8 byte. Okay.
Yeah.
Yeah, but we want to treat it like bytes, right? So one double is like 8 characters. It's okay in terms of size.
Yeah.
Yeah. So the address is the same. So the beginning location should be the same. So we are using the void style, which is like a general pointer. Okay, just like object in Java. It's okay.
Yeah, yeah.
This location. But when we append it, because this buffer is a character buffer, we need to convert it back to character. So that this buffer's insert function can call. It's okay.
Yes.
Yeah. All right. So and the constant means hey, well, we are just reading the content and append it, right? So we don't really need we don't really
Changes.
change the input. Okay, so we constant. If you change the input here, it will compiler will report error. Okay, the runtime will not check this. It's okay.
Yeah, yeah.
Let me clear a little bit. Okay, so it's a continue of this. Oh no, this is another file called communication knowledge. We just want to say how this is used, right? So for example, our ideal case, we want to send the data, right? And you give it the data, and we don't want to do a deep copy. So this is reference, okay?
Yeah.
We'll send from machine 1 to machine 2, right? So through a channel, okay? Right. So we will firstly create an empty serialization object, just like what we defined before, but the vector is empty right now. It's okay?
Yeah.
And then we will serialize things in there. It's okay?
Okay.
I'm not sure whether I just a moment. Let me see whether I defined this. Okay. Yeah, so we will define serialization operator overload later. Okay, so that you can serialize things there. It's okay.
Yeah.
Yeah. So we will touch upon this later. But anyway, so the reason we define this buffer is we want to serialize data in there, and it's saved in binary format. Okay. It's actually this is a wrapper of the raw bytes. It's okay.
Yeah.
And then we can send it out, right?
Yeah. But Professor, this tag is what you said channel.
Oh, this tag is a MPI channel, right? So this tag is basically this tag, okay? Because this function is calling this function, and it will call MPI send. And remember the get buffer from this.
Yeah.
And how many sides, right? It will send. And the MPI you can send the basic unit can be other items, right? So we always use char, okay? Because we already serialize into char object, okay?
Yeah.
From destination, from the current machine to this destination machine, right? Maybe I'm machine 1, I put 3, I will send to machine 3. It's okay?
Yes.
Okay. And then tag, so if between two machines, we have IP addresses, right? IP1, IP2, okay? But maybe you have two different applications, right? So maybe this application is, for example, Skype, okay? This is Zoom, right?
Yeah.
And you don't want the Skype package to be received by Zoom, right?
Yeah.
Okay. So you also need port number, right? So this sending port number is 1, this sending port number is 2, this sending port number is 3, this sending port 4, okay? Right?
Yeah.
So they don't interfere with each other, right? This is 1, 4, IP1, IP2 is one channel, right? So 2, 3, IP1, IP2 is another channel. So they know which application to which application. It's okay? So
Yes.
IP plus port number. So tag is like port number. It's okay?
Yeah. Okay.
Yeah, so basically you can have different threads, right? So we have receiver, we have sender, and we even have something aggregator, right? Main thread checks the synchronization, right? So maybe you have thread 1, you have thread 2 right, on this machine. You also have thread 1, thread 2 on that machine, okay? Right? Maybe thread 1 communication, we will use tag 1, 0, okay? Thread 2, thread 2, we use tag 1, okay? And if thread 2 communicate with thread 1, we use channels tag 2, okay? They don't interfere with each other. It's okay?
Yes.
Yeah, so that's the purpose, right? Let me see. I think I should. All right, so this is just want to say why you need to get buffer, get size, right, and how it send out, right? So you can see this send data is sending this, right? So finally, just put data, it will automatically handle things and send out, right? So you will also have something receive, right? So receive is calling the receiver by string, then you can get it, okay?
Yeah.
Yeah. So, but we are in single machine. We will not go to the communication module until later if necessary. Okay. We will expose the gsyncer code part by part. Okay. Only those you need. It's okay.
Yes.
And here we just talked about, right? So if you are just appending a character, right? If a character a double, right? So then this should be the beginning pointer of that 8 bytes. Okay. And this should be 8. It's okay.
Yes. Professor, one quick question now. For this serialization issue, is the order, I think the order is important of characters, right?
Yeah, the order is important, right? So because you are insert, you are append, push back, right? So if you first get A in there, then B, then it will be A first and then B. It's okay?
Yeah. Okay.
Yeah. For example, if you first say I want to get a character, let's say A here, okay? Then you will get A here, right? Right? And
Yes.
then you say then I want to using arrow to make a float here, right? Then you have a float here. It's all that matters. It's okay?
Yes.
Yeah. And another thing, although we are not talking about MPIs, this also matters. Okay. So on the one channel, on the same channel, the order matters. Okay.
Yes. Okay.
Yeah. So this is like TCP, right? So if your tag is the same, right, then the order matters. It's okay? If you first send through tag 0, A, then send through B, the receiver side will always first receive A and then B. Okay?
Yeah.
Yeah, but for different tags, it's different channels. So some earlier sending message will be received later. That's possible. Okay?
Yes. But Professor, why I'm asking this, maybe I have misunderstood something before this. Like my understanding to serialization, like for example, if you have a string and you serialize this in memory as a string, then it will be bytes, right? 0 and 1. No.
Yes. Yes.
So like my question here, when you push back in this buffer,
yeah,
we are actually pushing. I mean, my understanding that we are pushing 0 and 1, not characters, right?
No.
Or no?
Computer always work with so-called words, not bits. Okay, only network work with bits. It's okay?
Okay. Okay.
Let me see what I can.
You mean the stream is a stream of words, not a stream of bits?
It's logically bits, but it's always words. It's okay? Let me see what
bits, Professor.
What?
Isn't one word like 16 bits?
It's depending on your operating system, right? If you're 32, it's so it's different registers, right? So AX, BX, CX, DX, right? So the earliest is 8 bits, okay, which is in assembly language, right? So you have these, right? So if you ALU, right? So So when you do computations, the simple level is ALU, right? You have the registers. The register operates on words, okay?
Yeah, okay.
Yeah, so that's why you always do operations always on words, at least on the byte level. It's okay, maybe short, 2 bytes or 4 bytes or 8 bytes nowadays because operating system, right? It's okay?
Yes.
Yeah, you never operate on bits. Even if you want to, let's say, do this bit, the cost is the same as operating on these 2 words. It's okay? Because the basic unit is words. It's okay?
Yes, okay. Yeah.
Right, so yeah, okay. So there's also word alignment, right? So if you are, so like in C structure, there's a word alignment or something. I'm not sure whether the name is correct, right? So sometimes in order just to make the words align, so they will purposefully leave some empty space, okay? So that it's actually,
Yes.
right? If you use one bit, it will leave the other 9 bits empty or something, so that in the operating system, you can be aligned. Those registers can operate this for you, okay? Because
Yes.
one operation is on a word, not on byte. It's okay.
Yes. Yes.
Yeah. So unless maybe on network card, it's a little bit different. Okay. Right. So only if you just work on one byte, right? So maybe the operator, the register is 8 bytes. Okay. Why not do this, right? There's actually something called a vector register. Okay. In NVIDIA, right? So that means each operation they can operate on maybe 20 words, etc. It's okay. They call it vector register, right? And then you want to fill all those 20 maybe integers each time, okay? And then do one operation, okay? Because it's a one clock, right? In some sense, right?
Yes.
In one clock, you can do 20. Why do one? Okay, or even do 1 byte, right? It doesn't make sense. It's okay.
Yes.
All right. So I hope you have this concept. Again, all these are connected, but it really depends on whether your undergraduate teacher is teaching properly, right? So, okay. All right. So now these things are actually wrapped outside. Okay. So you can see double is just what we mentioned. The size of double is 8, right? And this is the address of this double. Okay. The first location will be convertible to star. It's okay.
Yes.
Right. And if it's just a character, then it's a raw byte. Others are raw bytes. It's okay. And we define all basic types so that they are defined. And because they are defined, when we use them, the compiler will look at this function when we are serializing into this byte stream. Okay. We don't need a writable wrapper like in Java. It's okay.
Yes.
Yeah. And if you have a pointer, right? So the pointer is an address. That makes sense, right? So we actually get the what you pointed to and serialize that thing there. It's okay.
Yes.
Yeah, so this is how our library design though. Okay, so which means you need to delete this. Yeah, so we will see there's some implication there, right? So basically we are saying that if you have a integer and an integer star, their serialized byte stream is the same. It's okay?
Yes.
Yeah, because we will get the body. And now if let's say for serializing the containers, right? Let's say vectors, okay? Right.
Yeah.
And we need to make sure each type T is serializable, like those we previously defined. Okay, right? Okay, or it can be more complicated, maybe a struct that is serializable, or even another vector, right? Because we make sure this function is to make sure if T is serializable, the whole vector T is serializable. It's okay.
Yeah.
Yeah. So in order to do that, what you do is you say, hey, first I write the size, right?
Yes.
Yeah, let's say we have 10 vector items, right? So first I write a 10 into the Python stream, and then we write the 10 items one by one. And this actually calls the T's, T's serialization, right? If your T is double, then we're calling this function. It's okay?
Yeah.
Yeah, right. It's a recursive call, right?
Yes.
Right. So there's in C++, we have something called a specificity, right? So if you let's say we have a vector int and a deserialization, and we can match this, we can also match this, right?
Yeah.
But int this is a narrower, this is more specific, right? So we'll always match the more specific one, not using this. Is okay?
Yeah.
Yeah. All right. So we do have some optimization for those basic types, right? Because for this basic type, we can using raw bytes, okay? Because you have this integer string, right? It's okay. Each is 4 bytes, right? But we can just say, hey, this is the starting location of the first item, okay, right?
Yeah.
And then how many items times 4, right? So maybe this here we have 5 items, but each is 4 bytes. We can say, hey, 20. Then this is the character array. Use raw bytes to write it out. It's okay.
Yeah.
This is way faster because you don't have to work with this iterator, those kinds of things. It's okay. So we do have some more optimized implementation for some of them. Okay.
Okay.
Yeah, so this is also the case if you look at C++, there are something like a vector bool, right? So vector bool is a bit array, right? Do you know that?
No.
Actually we did a training on that, but it's fine. We to look again. Okay. Let me switch to the mouse. Okay. Right. So vector bool actually using a single bit inside. Okay, rather than a byte, even though bool is a byte. It's okay.
Yes.
Yeah. So vector bool is specifically designed, right? So to be more space efficient, because using one byte and using one bit is the same, right?
Yeah.
The
Yeah,
benefit
yeah.
is that now in one instruction, right, you can operate on 8 elements, not one element. It's okay?
Yeah.
Yeah, so you understand the benefit, right? And it's more space efficient, right? So previously you need an 8 byte, not only 1 byte
Yeah.
to store it. Okay, this is more specific. So
Yes.
whenever you go to vector bool, it will go to this. And if it doesn't match, then it will go to vector t. It's okay?
Yeah.
Okay. Let's see where. All right, so this is following the same ideology. Okay. All right, so previously we are talking about something you can write into, right? So now if we receive it from network, right? So we want to serialize it out, okay? Right, so we need something
Yeah.
asymmetric, right? So something like this, okay? So now, because when we receive something, we will always know its size, okay?
Yeah.
So there's no point to push back in using vector, right? Vector is, it manages the size for us with some additional cost, right? Like
Yeah.
capacity is a little bit larger than size, but we don't need it in deserialization because we exactly know how the block of data we need. Okay.
Yes.
So this we are doing is a dynamic array with a character here and what's the size. Okay. Right. So basically,
Yeah.
I have a block. Then I have an index pointing to location 0, and whenever I read an integer, I move this index maybe 4 forward. Okay. Maybe the next time I read a float, I move 8, and the index comes to
Yeah.
this location. It's okay.
Yes.
So initially the index is 0. It's okay.
Yeah.
Yeah. So our design is something like this, right? So you let's say you receive a buffer and you create a buffer, okay,
Yeah.
outside, and then you throw to our upstream. But our upstream will then delete it for you. It's okay. After use.
Yes.
Yeah. So
Yeah.
this is another kind of design that you don't need to. You still need to match new and delete, but actually, because the delete is handled by this object, all you need to do is new something and give it, right? It will delete it for you when it's used. Okay, it's more like a delegator. It's okay.
Yeah.
Yeah. And so we also have raw bytes and raw byte, these two. Okay, but this is a little bit different here. Okay, so this is now we have this and we read to this location, right? If we raw byte, we do the next one and move this forward. Okay, right. So buffer the current location and move the index forward. It's
Yeah.
okay. Yeah, and the raw bytes is the same, but move so many bytes. It's okay.
Yeah.
Right. Any questions?
No, it's okay.
If the others have a question, you can also ask. Okay. All right. So how is this used? Right. So this is how it's used. Right. We will receive something. Okay. Then what we will do is we first, hey, who is sending me MPI probe? And if I know who is sending me, hey, how many you want to send? Okay. And I will get into this size. Right. So unfortunately, MPI, this library is a C library. So they don't have the reference. So you have to give a pointer of this thing, right? Which means the address of this thing. Okay. Right. It will write this how many bytes to you. It's okay?
Okay.
Yeah. And once you get the size, you can create a buffer of this size, right?
Yeah.
And with this size, then you can say, hey, I want to receive so many into this buffer. It's okay?
Yes.
And once we have this, we can create this. All right. So in C++, if you return a unnamed object, the anonymous object, right? This thing will not be a deep copy. This thing will just throw directly to your this constructor will be, so basically if you're returning this function, right, it's popped out, right? But this object will be directly created into the previous stack. Is okay?
Yes.
Yeah, even though this is and then we just collect it. Okay, this basically says you are creating to this. It's okay? This is more like a constructor. So this is a special use of C++. It's okay?
Yeah, it's like a wrapper, right?
Yeah. So it's because this is different from if you create something local called A, and then you create A this, right? If you do this, then this A is in this place. If you delete it, it's not there. It's okay, right? Yeah. And if you deep copy, then when you deep copy here, this thing is not there, right? So this named constructor is different, okay, right? You know,
Yes.
so it's more like a new something if it's a pointer, right? No, now it's an entity, right? Entity is something a little bit special use. Okay, so I need to point out, okay?
Yeah.
Not a regular use. But anyway, so when you receive data, right? So you say, hey, I want to receive data from this machine, right? From this channel. Okay, I will receive some stream, right? And this stream, we will call this function, right? We will say, hey, how many size you want to send me, okay? And create the buffer and then get the content. It's okay, right?
Yes.
And remember, this basically constructor will throw this, and the deconstructor will delete the container for you. It's okay.
Yeah.
Which means now this new operator's stuff is now here, and when I run to here, this guy is deleted, right? So we will delete this space for you. Okay, so that no memory leak. Is okay?
Yes.
Yeah. And now all we need is create a data T and a serialized T. Okay.
Yes.
And keep in mind, this T can be super complex. It could be a vertex with a bunch of adjacency lists and additional item, and maybe you can keep a map, etc. Okay. And this serialization is recursive, right? It will recursively go down. It's okay? And serialize for you, right? So you can have a very complicated thing wrapped in one object. For example, let me see. Maybe we didn't show that, but if we click this, let me go to the browser on this screen. Oh, no. Yeah, because we did show raw bytes. We didn't show how this is used, right? So if we open it here, right? So this is what we just see, okay?
Yeah.
Yeah. And this raw bytes is similarly used like this here. It's okay? You see? So for example, if you have 1 byte, right? So you will calculate a raw byte. It's okay? This is the index plus 1. It's okay?
Okay.
Otherwise, you will have raw bytes. It's okay?
Yeah.
These two, right? Index. So here is, for example, if you look at this, basically with raw bytes, long is maybe 8 bytes. Okay. So what we will do is we will put 8 here and bytes 8. Okay. Right. And then we will move index by 8. Right. Before doing that, of course, we need to return the buff. Right. So let me see how to do this.
Maybe this is defined in the constructor.
Yeah. So this index is the current location, right? So for example, this is your buffer, okay, right?
Yeah.
This is the current location, which is the index, okay?
Yeah.
Now this segment is your double, okay, right?
Yes.
So we just point the first location return, and then we move this thing forward to here. It's okay?
Yeah.
Right. So that's what it is doing. Okay, and of course, because this guy returns void star because you want to match any type, you need to match this type and map it back. Then it becomes a double and copy to here. It's okay?
Yes.
Right. Yeah. So that's so another important thing that may be more important for us is IO SER.h. Right. So this is the disk stream. It's okay?
Okay.
Yeah, let's open it so that we have it here.
So this is a professional disk stream to save as files on disk, right?
Yeah, it's more like a IF stream, OF stream, but with a buffer, okay? So that we don't store a terabyte, maybe just a 4 KB of data in memory, but we will be able to manipulate them and serialize in, serialize out, okay? Serializer is always one way, one directional, okay? You cannot go back.
Yes.
Right. Okay, So used for saving spilled tasks, right? So this I didn't mention why we need spill tasks. I finally just realized we still need to spill tasks because we one task can be too big and call maybe 10,000 add task, right?
Yeah.
And in that case, in our application, 10,000 tasks will be added into our in-memory buffer. Then it's go beyond the capacity and too much space. It's okay?
Yes.
Yeah, so this we still need to handle. Originally, I'm not considering this, and previously I'm just considering it's not remote system, right? So there will not be a lot of things suddenly be ready, right? But this task itself, when computed, can have many child tasks insert. Okay,
Yeah.
so if we have too
Yes.
many, some of them need to be moved to disk. Is okay?
Yes.
So this is another file called ioscr.h. It's similar to scr.h. Okay, it's just that we are saving to disk, right? Let me see the time. Okay, we should still have time because we have a meeting at 1, right? So let's move a little bit quicker. So so we have a memory buffer, okay?
Yes.
And this buffer has a fixed size, which is of this size initialized. It's okay. So we'll not go beyond maybe 4 KB. It's okay.
Okay.
So the memory consumption is fixed, right? And so there's a buffer position. This is the buffer position. When you read, it will move on, just like our buffer position originally. Okay.
Yes.
But keep in mind, this buffer is just a sliding window of a big file. It's okay.
Yeah.
So we also need to remember where you are in the file. Let's say right now we are at this location. It's okay, right?
Yes.
So with respect to the buffer, right? So this buffer pose with respect to the buffer, this is your value. It's okay.
Yeah.
But with respect to the file total position, this is your value. It's okay. This is your file location.
Yes.
All right. So these are the definition of these two variables. Okay. So initially both are 0, and you create the buffer, right? So when you open, you will open the buffer. Okay. So yeah. So the initialization constructor. Okay. And you usually give a file name here. Okay. And the important subfunction is called a buff flush, right? Because when you write, and the buffer is full, right? So when you write, the buffer is full, okay? Right? Because this is a writing buffer. Okay, we will see the reading buffer later. When it's full, what you do is you flush this to the file. It's okay?
Yes.
So the file content basically is considered what you already flushed plus what is right now in the buffer, okay?
Yes.
Yeah. So when buffer is full, you flush this to the file and then empty it, which means you move the buffer location to the beginning. It's okay, and then you can continue your time.
Yes.
Right. So this is a serializer. Okay. And the flush is just doing this, right? So you get the current position and you get the current position in the buffer, right? So let me see. So what you do is firstly, so what you really want to do, let me see, is from the memory location, because this buffer you have used this right now, you're here, right? So the memory position is here. It's okay.
Yeah.
I flash you what's the rest of the space, right? Okay. The basic unit is a byte, one byte. It's okay into the file. So we are this is what we are doing. It's okay.
You said, Professor, 1 byte.
Yeah, so this is the fwrite function. So each basic unit is byte. It's like an MPI chart. It's okay?
Okay.
Yeah, and how many elements? This is rest. How many still remaining? It's okay?
Yeah.
Yeah. So let me see. So what we will do is we will write this, right? So initially we will write this, okay? Right, because if you look at here, counter initial is 0, so this will not enter, okay? And we will write this, okay?
Yes.
Yeah. So I think this is end position. This is the beginning position. Okay, this is end position. It's not the the size, okay? Because when you this pointer reach this pointer, we end. It's okay. So this end position is last location. It's okay. This is the current location, right?
Yes.
The current pose is the buff pose, okay? But sometimes this function doesn't function properly, right? So you need to say, hey, I want to write so many bytes, whether the bytes is the same as the bytes I want, okay? Right.
Yes.
Oh, sorry. This is actually the remaining. So because initially this rest is buff because your starting position is 0, right? Your starting position is 0. Of course, your remaining is the whole thing, okay? The size is okay.
Yeah.
So you will initially write this, but sometimes it says, hey, it's not equal to what is remaining, okay? Right? There's some writing error or something. So we do some loop, okay? Otherwise, it's actually just this thing itself. It's okay.
Yeah. Yeah.
So you can ignore those, and then this is just a protection because sometimes we find it fails. Okay, maybe the disk issue or something. Okay, you can just treat it like something like this, right? Okay.
Yeah. Yeah. Okay.
Okay. Any questions?
No, it's okay.
All right. So keep in mind when we have this buffer, most of them are flushed into disk. The memory may still have some content here until the current position. It's okay. Right.
Yes.
And when we finally want to close the file stream, this thing should be flushed here. It's okay.
Yes.
So we just see whether this location is not 0, right? If it's larger than 0, we need to flush. It's okay.
Yes. Yes.
Right.
This is in the
Yeah.
in the deconstructor.
Yeah, and this buff pose is this position. We will flush this content out. It's okay.
Yeah.
Right. So and then we will close the file. Okay, and then see whether it's good. And finally, we need to delete the memory buffer. Right. Otherwise, it will be garbage. If we do this IF stream many times, each time we will leave this amount of garbage in memory. It's okay.
Yes.
Any questions?
It's okay.
Let me see what is here. So likewise, we have raw byte and raw bytes, right? But it's a little bit more complicated. Okay, so here we have these, and then we also have the raw bytes. Okay, it's a little bit more complicated because now, the first thing you see is whether my current buffer is full. Okay, right? If I'm already here, let me see why. Yeah, okay. If I'm already here, right, and then I want to write another character, this will be buffer overflow. It's okay. This is not allowed, right?
Yeah.
So what I will do is if I'm already at the end, I will flush it and move this to here.
Yeah.
This content already go to this, right? And then I append this C. It's okay. Right.
Yes.
Then this becomes location 1, and in the file we also move this by 1. It's okay. Right.
Yes.
And this flush will handle the total plus. Okay. Internally they also plus that. It's okay.
Yeah.
Yeah. So and let me see. Oh, actually, not really necessary. The total is always following buff, right? So the buff is already there. So buff flush doesn't have to add that. Okay, so that's I don't think what I mentioned is correct. So now let's come to raw bytes, right? We want to write a bunch of bytes. It's okay.
Yes.
Yeah. So now there's a size like the 888, right? So this is something.
Yeah.
Like okay. And what we need to do is, our current location is buff pose is here, right? And we know the total is this, and we know what's the gap, okay? What's the remaining?
Yeah.
Okay. But importantly, if what's remaining is not enough, right? You write a string that is very long, right? And you want to write a string like this, it will overflow. It's okay?
Yes.
Yeah, so that's why we are handling this, okay?
Yes.
So what we will do is we will flush whatever remains, right? So, this guy will go to disk. It's okay?
Yes.
So this is what we are doing. We'll flush, right? Whatever is remaining. And so of course this PTR is a void style. We need to make it a character style. Okay, then we can call this. Okay. And then what we will do is we will, now this is flushed, right? Originally this is, this is also used, right? Okay.
Yes.
Yeah, this is also used. So we are basically, let me see. Mm. Oh, what I mentioned is wrong. Okay, so this is doing this. Okay, so this is memory copy, which means our buffer pose is here. It's okay,
Yeah.
right? And you want to have a very long string. Okay, right, like this guy. Okay, this is
Yeah.
the string which you have, which is here. Okay, and now I can only copy this, right? So which means this copy to here. It's okay.
Yes.
This is what this line is doing. It's okay.
But this is Professor. This if statement here, if only the size is, if only the gap is less than the size, right?
Yeah, if you know this guy you write is very small, you can just move this forward. Okay, just do a simple memory copy.
Okay.
It's okay.
Yes.
Move it. Yeah. So this is. But if you will, if you copy it here, this will go beyond the buffer. That's not okay, right? So we first copy this here. That's allowed. Okay, right?
Yes.
And then we flush the buffer into disk, so the whole content is now appended to the file. It's okay.
Yes.
And then we kind of move this back to the beginning and we continue. It's okay.
Yeah.
And unfortunately, maybe this string is so long, maybe the whole thing fills the next buffer. Then we need to find while loop until the last gap can fix in here. It's okay?
Yes.
So this is basically the logic. Okay, you don't see we move the buffer forward because, you know, in the beginning of the while loop, it's always in the beginning. Okay, right? So you use a whole batch. Okay, so you can read the details. I will read the details.
Yeah, sure.
So if you want, but actually you don't need to read the details. You basically, the purpose of this is to let you know what is there. Okay, so let me close it temporarily. So this is wrong. Okay, we cannot have this. This comment is wrong. Okay, so then you can confidently use it. Okay, that's all the purpose, because you will not change it. So you don't need to understand this part so deep.
Yeah. Okay.
Right. So the reason is these are actually fine. Okay, these are raw bytes are actually fine. So because our raw byte already handles the overflow. Okay, right.
Yeah.
Raw bytes. These look pretty much fine. Right. So because we handle the overflow, then you can just call like before. Okay. They will, when it overflows, it will go to disk. And the other direction, right? So if we already know how many we want, we have a memory buffer, right? So and we know the file we want to stream in. Okay.
Yes.
Yeah. So we can only have so much size. Okay. When we read, we can only fill this block. Okay. The rest of the content should remain the file. It's okay.
This is Professor reading here.
Yes, this is reading. So we have an in-memory buffer, okay, of this size. So each time, even our file is so long, each time, the first time we refill, we just fill this into the file. It's okay?
Yeah, okay.
And when we use, right, we read this, we move forward. We use to here, we have nothing to read anymore. We refill the next block here, okay?
Yeah, okay.
Okay, so this is the logic. I will move a little bit faster because it's not so interesting.
Yeah, sure. We don't need maybe to go to, deep details. I will read this.
Yeah, so if you want, you can read it, but just to give you confidence that it's correctly written and fully tested. So no worry, you understand the logic, then you can use it confidently, okay?
Yeah, okay.
You don't really need to understand every, these location, how move around. Okay, so they are tested and they are well written, okay?
Yeah, okay.
So you get to the high level idea, that's fine, okay? We will have the task for you later in later slides, okay? Maybe 30 something or 40, okay? Yeah. Okay, so for the raw byte, it's very simple, right? So just like what we said, so firstly you will add the location, okay?
Yeah.
Right. So because now you write a byte, right? So you read one more byte. Of course, your file location is plus, okay? Right.
Yeah.
But when you get to the memory location, it's become tricky because maybe your memory location you read, you're already here, right? Okay.
Yeah.
Then you need to fill. You call the fill, which means you load another block here and move this beginning, and then get the first location. It's okay?
Yes.
Despite everything, right? And this raw byte is a little bit more complicated, which means you if you continue to read, an item cannot pass the buffer capacity, right? So here, just give you some high-level idea. Okay, so when you read so many bytes, right? Let's say your buffer will read until here. Now you want to read this, and this will go beyond here. Okay.
Yeah.
Then you need to handle that, right?
Yes.
Yeah. So in order to handle that, you need some additional processing. Okay. So basically, you see whether the buffer size minus buffer pose, there's a gap, right? And this gap is more than what you want to write. If yes, you simply do this in the memory buffer. Okay. Right.
Okay.
Otherwise, you need to handle it, right? So you need to do on disk. Okay. So here, give you a brief idea of what we are doing here. Okay.
Yes.
So because you want to read the whole thing, right?
Yes.
But we cannot read the whole thing, right? We don't have so many space. So what we do is this. We'll copy this thing to the beginning, okay? Because these things are already wrapped, no longer useful. We'll copy it to the beginning. This is what we are doing here, right? This is the beginning location. This is the current location, okay?
Yes.
From here to here. And the gap location, okay? So many bytes. It's okay?
Yeah.
And then we will read the remaining, right? Read a bunch of here that can fill this. It's okay?
Yes.
And then we will return. And then you will get this as what you need. It's okay?
Yes.
Let's say this is a 1 byte remaining, but we want to read a double, then 7 byte will be read here. This first byte will be moved in the beginning, and then you can get this memory location, and then you can read this, copy this into your double. It's okay?
Yes.
But this doesn't hold if you think about it. If your entire object goes beyond this size, then this still doesn't work. It's okay? Right.
Okay.
If it's double, it's fine. If it's a string that is double size of your buffer, right? Then it doesn't work, right?
Yeah.
Yeah. You understand what I'm talking about, right?
Yeah. Yeah.
Yeah. So that's why we need some additional handling. Oh, there's one requirement: memory copy. The source and destination should not overlap. So this is what we are doing. So because source and destination cannot overlap, we require when we copy, right? So we can copy at most this size to here, then they don't overlap. Okay, you cannot copy, let's say A, B, C, D, E. Okay, you cannot copy this segment to this, like B, C, C something. Then there's some overlap. It's okay.
Oh, okay.
Yeah, so this is required by this function. And actually, originally we didn't notice this small requirement, and then use the valgrind, we catch the error. Okay, just point the issues. Then we come back and find this issue, and we fix this. Okay.
Okay.
So when we fix this, we use half buffer size so that we make sure the copy doesn't overlap, because the raw bytes cause a copy. It's okay.
Yes.
This is raw bytes, right? So this is one small details that can cause bug. Okay. So then serialization of those things should be fine. Okay. Right.
Yes.
If their size is small, but if you you have some objects. So basically, these objects are not as we know our buffer will be more than 8 bytes. Okay, right?
Yes.
And so when we move this last byte to beginning and read additional 7 bytes from the file, we know this will be okay. We give the starting pointer, it will be okay, right? It will not go beyond here. It's okay.
Yes.
Yeah, but for some of them, like a vector and a string, it will go beyond. It's okay.
Yeah.
Yeah. For those, we need another while loop. Okay, and each time we get a half buffer size copied into our string, appended to the string, etc. Okay, right? Vector we need to insert. It's okay, part by part.
Okay. Yeah.
Right? Because maybe your vector or your string is so long, right? So 9.5 is the size of the buffer. This is possible. Okay, we still need it to handle properly, right? So instead of we give a pointer, hey, this is your vector, right? You cannot do that. You just say, hey, this is part of your vector, right? You insert into the back, okay? And then we reload another batch of and you insert again. It's okay?
Yes.
Yeah, so this is just to give you a high-level picture of what we're doing, raw bytes. Okay, so this is a little bit more complicated, okay? But this library is well tested, okay? Just use it, it's fine, okay?
Yeah, okay. Yeah.
And so here's example how we use it, right? So here is, for example, our application, right? Subgraph application. We have a vertex, and this vertex will be sent over the network, right? Sometimes you load the graph and the hash ID sent to another machine, right? Because that machine should handle the vertex, but you read it from HDFS from this machine, right? You need to send the vertex. It's okay.
Yes.
Yeah. And additionally, maybe you have the adjacency list in the vertex. You need to request from another machine. But maybe you are doing simple graph mining. Hey, this neighbor is not here. I request from you. So this will be sent over the network. It's okay.
Yeah.
So we need to make sure this vertex is serializable, right? So we know that this vertex has two objects like this, okay?
Yeah.
And we use a guarantee key T and the value T should already be serializable. It's okay?
Okay.
If that's the case, then they should be, we just do a recursive function of this, right? So we first serialize ID and serialize the value, okay? Right, and then this can be I be stream, O be stream memory. This can also be on the file, okay?
Yes.
Yeah, because our task may also have something like subgraphs. So if you click this, let me see. Why it's not coming up? Oh, I think it's because I'm using. All right. So for example, this vertex. Let me see. Previously, what we see is vertex.h. Okay. Vertex h. We can also have like a subgraph, right? So subgraph it should also have something like this. It's okay. So they can both be saved to file and sent over network. It's okay.
Yeah.
Because the subgraph itself contains a hash map, right? Hash map of V map and vertices. So what it does is just serialize V vertices. Okay, hash map will be created online, so we don't just send it because hash map can be created from vertices. We can save some memory, save some network bandwidth. It's okay.
Yes.
Yeah. So this is quite flexible. So once you have you serialize back, you will create the hash map according to the vertex, right? With one folder. Okay. Right.
Yes.
So all that is required because you can serialize the vertices because the vertices what is a vector of vertex IT, right? Vector T. The vector T we just see it's serializable in a previous slide, and vector T is serializable. Okay, we define these functions, so we can serialize this. Okay, and then
Yes.
the subgraph becomes serializable, and we know that the subgraph is part of the task object. So then the task object becomes serializable. Right. We want to do work stealing. We will steal tasks. It's okay. Right. It has a subgraph, it has additional fields, and the vertex you want to do, right? So see that it's field. Okay, it's all like this kind of recursive definition. You will make things that can be sent over the network. It's okay?
Yes.
All right. Just a moment. I received some email just to do a small check. Okay. Yeah, I think I have quite some email to handle. All right, so, and this is compared with Hadoop, right? So Hadoop doing something similar, right? So if you have an object yourself, right, like a key value pair, right, a value, right, which is my writable type. You have an integer, you have a long, like a struct in C, right? And then you need to say, hey, I want to write out my integer, my long, because they're writable, okay? Int and long writable are defined, okay? And then once you define these two functions, right? This is a write, read, right? And then you can serialize this object. It's okay?
Yes.
The only difference is that in Java, you need to have an interface, right? Or you use its native serializable interface, but that one is crazy. Okay, it's not compact. It's okay?
Yeah.
Yeah, because if you look at here, if we serialize those things, it's really just a size of the container plus all the items. If an integer, then it's 4 bytes, 4 bytes, 4 bytes. Okay, for Java, it's crazy. It's serialization is just too bad. Okay, so they do another writable interface in Hadoop. Is okay?
Yes.
Right. All right, so that's pretty much for the serialization part. Any questions?
It's okay.
Yeah. For Sami and Latif, can you follow this?
Somewhat, sir. Yes, thank you.
Okay.
Probably have to review the videos, but I think you were talking about the gthinker buffer stuff. So I somewhat follow it. Yes, sir.
Yeah, some of the libraries are independent. It's more like a vector or your hash map, this kind of thing. I'm not talking about, because gthinker uses these written by us. Okay.
I see.
Yeah. So we're talking about the modules, but we just point to gthinker link. on those modules.
Okay.
When July need to use it, July just copy
Mhm.
those files out, whatever header file you need. It's okay?
Yes, sir. Thank you.
Okay. All right, so July.
Yes.
Yeah, so now it's a task for you. So if Sami and Latif who want to leave, that's fine. Okay, no worry. If you want to continue listening, that's also fine. Okay, depending on your arrangement of time. So here,
Yeah, I have to leave now.
Sure.
Thank you.
You're welcome. Yeah. Okay. So Jalal, you have implemented this this framework, right?
Yes.
Yeah. So basically, you have the task queue, which is just a queue. Okay, right? The STD queue.
Yeah.
And you have a bunch of threads. And I think have you removed have you moved the initial task to the worker class?
Not yet, Professor. I was working on the other
Yeah.
project, but I will do this maybe today.
Yeah, just keep it on the list so that you will remember to move it. Okay.
Yeah, I have it. Yeah. Okay.
Professor, should I stay or do you want me to leave? It's up to you. I don't know.
If you want to listen, you can stay.
Oh,
If
okay.
you have something else to do, like Latif, then feel free to leave. Okay, no worry.
Oh no, I only am working on the generator. So if you're free today, maybe I can set an appointment. Need to ask some questions, but maybe
That's
later.
fine. Yeah, that's fine. But I have a meeting from 1 to 2 maybe. Okay, so you can make a. Let me see what other meeting I have. Just.
I'll probably then make an
Oh, I have
appointment.
another meeting 5 to 6. Otherwise, the time is
Okay.
open. Night time is
Okay.
open. Okay, feel free to.
Okay.
Right. Yeah.
Okay. Thank you for your time, sir. I
you're welcome.
appreciate it.
Yeah.
Thank you. Have a good day, sir.
Okay. See you then. Yeah. Okay. All right. So Jalal.
Yes, Professor.
Yeah. So we have two tasks. Okay.
Okay.
The first task is a priority queue, right? So we need to change this queue to a priority queue, right?
Okay.
Because you were in the tutorial, right?
Yeah.
Yeah, so you know that our G-Sync VLDB paper basically make a priority to the tasks, right? Expensive tasks run first, and they can decompose, and then can add more tasks here. Then other people can work on this task, right? In parallel.
Yeah.
Right. So right now we are not having this, so we need to change this to a priority queue. It's okay.
Okay.
All right. So the second is that we need to consider divide and conquer of one big task into many small tasks. So we need to consider task splitting to disk. It's okay.
Yes. Okay.
Yeah. So this is now where you really need to understand. The previous I just introduced a library to you. Okay.
Yeah.
Yeah. Here is what you really need to handle. Okay. So these are the two tasks that you need to add to our current framework. Is okay.
Okay.
Yeah, I will follow up with Gwynmo. I don't want to push him too hard, so maybe Friday, see whether his API is ready. So if you can make this part already, then we can push a little bit this project. Okay.
Yeah. Okay.
Because after today's meeting, maybe we can temporarily work on this project for one week because we are by week, right? So then the other week you can work on Virginia's project, for example, right?
Yeah.
Yeah. So we push this a little bit. Okay. So because I have potentially 5 more papers in January. Okay, so
Okay.
to work
Yeah,
on.
I understand.
In addition to this, so I understand the deadline is January the 31st, right? But I cannot wait for so long. Okay, because for each week, basically, I need to work on at least 1 to 2 papers. Okay, we can left half of the content later, let's say the experiments, right? And then you proofread those. We can work on the last moment, but the main body, I want to make it ready by this month. Okay, maybe 20, early 20s or 20 something. Okay, right?
Yes.
Then I will leave it to you. You work on it. I will first write a draft in LaTeX, and I will throw the LaTeX to you. You work on the LaTeX itself. Okay, right?
Yeah. Okay.
To improve and add experiments, etc. Oh, you want me to work on it? Fine, but let's communicate, see how things goes. The first version of LaTeX, I will show a demo to you. Later, you will probably write your own, especially for level 1, for example. Okay, right?
Yes.
Yeah. Okay, so let me see. Yeah, so we have these two tasks. One is we need to spill to disk if necessary, right? Which means when you refill, you also need to refill from disk, not just from the data array that you have right now. Okay, so that part also needs to be handled. right? Another is the task queue should be prioritizing big tasks. Okay, so here you see right now you have a queue, right?
Yes.
Okay, and if you go to our gsync comper, it's actually a DQ. Okay, it's a DQ.
Yeah.
So the reason is because I will talk about the reasons shortly. So this is DQ task queue. Right? The type is task D, and this becomes the task queue. Okay, and then people are using. And one thing you need to note is that we don't need to protect it because each comper has its own queue. Okay.
Yes.
But this is different from your case. Okay, your case everyone shares the same global queue. It's okay.
Yeah.
Yeah. So we need to protect it. Okay. So here is the logic. So this queue task is every thread, every CPU, every thread has its own queue. Okay, right?
Yes.
And this is DQ because DQ basically the circular queue, right? So circular array. You can move something from the back. Okay.
Yes.
And you can also move, insert something from the front. Okay.
Yes.
And remember, if we find a full, we will move the last batch of file tasking to the
Yeah,
front,
to this.
and we need to refill to the beginning of the queue. Okay, right.
Yes.
So this arrow actually wrong. We should move to the beginning of the queue. Okay, right. It's a DQ, right?
Yes.
Yeah. So we have two data structures that you can check out yourself. Okay. Actually, I can present it, but it will be another presentation, right? So maybe half an hour.
Yeah, maybe I can read this first, and then we can meet if you like.
So basically, the reason I don't want to put too much time on this is because it's simply the structure that is provided for you. Okay. So this is called a concurrent queue, right?
Okay.
So what it does is it has the two pointers. One is beginning, one is end. Is okay?
Yeah.
So this allows you to move, from both sides without conflict most of the time. Okay.
Yes.
Yeah. So this allows double the bandwidth throughput compared with if you have a vector or a queue that is mutex locked. Okay. Because we have two lots. Okay. Sometimes we just need a push front, push back. So there's no conflict when you insert something and you also take something. Sometimes it can happen in parallel. Okay.
Yes.
And actually, we have a URL for this algorithm description. Okay.
Yeah.
I'm not sure whether it's still here. Yeah, it's a Chinese, but this is very well described. Okay, why you see, this is basically everything is here. Okay, so what you can do is you translate into English, right? So you can translate into English and then you read it. Okay, and yeah, this is very well written. Actually, introduces this conq how it's designed. Okay, right.
Okay.
Yeah, so this is conq.
Now, Professor, one quick question: like, why do we need the queue to be like to read from the front and the back? Why not just a normal queue?
Yeah, so it's because this list we are implementing using this queue. Okay.
It's what?
So this file list is implemented as a conq. It's okay.
Okay.
Because you see, sometimes we want to append to the tail, and sometimes we want to fetch from beginning. Okay.
Okay. Okay.
Do you answer what I mean?
Yeah, like these files are
append to the file, right? So sometimes you want to take from file. Okay. This list pointers, and you can happen in parallel. It's okay.
Yes. Okay.
Yeah. So this is a data structure conq. Which I actually put in the previous slide, the conq. Okay, and this conq, then that's where we care about, right? So this is let me see. This is line 89, right? So if you look at line 89, you see this is a global file list. It's okay. Conq string, right?
Yes.
String is a file path or file name. Okay, I think it's a file path maybe. It's okay. Then you have the file. Yeah, so basically, you point to each file path, right? You don't keep the actual file. It's a metadata. You can use the name or the path to get the file to load later if necessary.
Yes,
It's a
yes,
list of strings. It's not a list of files. Okay. Each
yes.
string can get the file. It's okay. So this is
Yeah.
yeah. This in global.h. We also have a global.h. You can do something similar, right? Okay.
Yes.
Yeah. Okay. Okay. So remember, if we come back to, we have several paths that we will talk about. The first path is we want to load something from the file. It's okay.
Yes.
The second is we want to load something from your data array. It's okay.
Okay.
This is all refill, right? But we will first refill from file because they are not finished yet, right? If this already not finished, we still create new stuff. You just have more things pending on the disk. Okay, your disk will be
Yes.
full, right? So we'll first try to get things here. If there's nothing here, we get from here. It's okay.
Yes.
And finally, we want to move something to the file if necessary. Okay, on the disk.
Okay.
Yeah. So these are the functions we were talking about. This is moving from a file to the task queue. It's okay.
Yes.
Yeah. So this is from the global file list and DQ, and we will get get the see whether it succeeds, right? So if it succeeds, this string, I think there's a reference. Okay, so the content will be copied into here. It's okay, right?
Yeah.
And if this string is here, then we'll read this file. Okay, right? And serialize the task into it. And keep in mind, this is what? This is our iOS.h. It's okay?
Yeah.
Yeah, so you need a iOS.h. Okay, right? And then after reading till the very end, it's closed. It's okay?
Yeah.
Yeah, and keep in mind, so we need to remove this, okay? Remove, because
Yeah.
yeah, so I'm giving all the details. So basically you can refer, for example, if you load this block of files read to here, now the task is here. You definitely don't need them here. It's okay?
Yeah. To clean the area.
Yeah, of course the queue is handled, but the file content is still here, right? You need to remove it. Otherwise it will, you never, this is garbage collection, okay?
Yeah.
Let me see. Okay, so the next is of course append something else, right? But before talking about that, we need to look at add task. It's okay?
Yes.
Yeah, because we will add task one by one. But the add task itself has something special, okay?
Okay.
So keep in mind that right now our task queue is a local task queue, right? Okay.
Yes.
So we don't need to protect it. Actually, we later we need to protect it, okay? Right? Because our queue is a global queue,
Yes.
unlike in gsync curve. Okay. So actually, I think because this is calling add task again, what I'm thinking is that you can either make add task atomic, right? It will get a queue, but if you think this is too expensive, right? So you can also add a lock here, right? So you can add a unique lock here, right? So that's an object that will lock and then unlock when you get here. Okay, if you remember that.
Yes.
Yeah. Okay. Yeah. Another way is you can add the unique lock here, right? So then it will lock and then unlock here. Okay, because we access the Q task so many times in here, right? So we need to lock it when manipulating this, right?
Okay. Yeah.
So our add task logic is very simple. I think so remember we have three batch of capacity of 3C. Okay, the last C will be moved to disk if it's overflow, which means your capacity reaching 3C. It's okay, right?
Yeah.
And then if it's less than 1C, we will refill. Okay, after refill, it will get close to 2C. It's okay, right?
Yes.
Yeah. So this is our logic. So if we find, hey, it's already full, right? It's already full. Okay, and you want to insert a new task, you cannot do that. It's okay.
Okay.
You need to flush the last 2 disks and then append. It's okay.
Yes.
So if this is the case, you spill the last batch. Otherwise, you direct go here. Okay, this is push the task. It's okay.
Yes.
Yeah, and the spill is also very simple. If you look at it, this is what we do, right? So we will get the file name, right? So there's some global thing here happening. Basically, this is to get the file. Okay.
Yes.
Yeah. So get the file name and set file. I don't remember the details. So basically, this is to this is to create a new file and flush to disk. It's okay.
Okay.
But keep in mind, we cannot have the file of the same name, right?
Yeah. Okay.
Yeah. So each time we need to move the a file pointer forward. Okay. Right. So this is the first file, this is the second file, etc. So this is to create a new file that is not of the same name as all previous files. It's okay.
Yes.
Yeah. And getting this file name, then we can create a new file, and then we just keep flushing, right? So flushing this until the capacity become no more than 2C. It's okay.
Yes.
We get it back, and we serialize to out, right? This out stream, right? This is using the IOSCR, okay? Right.
Yeah.
And keep in mind that we need to delete it. It's okay.
Yes.
Yes. Otherwise, you get to the disk, then your memory should no longer have it. Otherwise, it's a garbage, memory leak. It's okay. Right.
Yeah.
And finally, this file should be appended to your global list. It's okay.
Okay.
And this is a conq, so it's fine. You don't need to protect it. Okay.
Okay.
Yeah, it's a concurrent queue. It will handle this, right? They have the locking internally. Okay. And so previously we talked about the reason we are talking about add task is because file to queue has add task. Okay, right? It's add task.
Yes.
Okay, and then if we come to here, right? So again, so we are not talking about locking protection yet. Okay, so maybe outside the add task, we need to add a lock whenever necessary. Okay, if you are one thread, you call this add task multiple times, it lock it and call the file to queue. Okay, right? And here, if you that's rather you just add your task once, right? I think add a lock queue task here will be the easiest way. Okay, right? Make sure the queue is accessed atomically, right? Okay.
Okay.
Because here it does not directly access the queue, right? It's called add task to access the queue. But this may be inefficient sometimes. But we will see. Okay, you can add a unique queue here, right? Because here the compiler have local queues, so in gsync we don't protect it. It's okay.
Yes.
Yeah. So because you think about it, it's kind of inefficient, right? So the reason we are adding task file to queue is because we're refilling, because we have less than C. Okay.
Yeah.
But in the meanwhile, if we allow something to beyond 2C, that we are flushing. It's like in the meanwhile, we sometimes we are loading, sometimes we are spilling. It's like inefficient. We can discuss how to implement this later. Okay, right?
Yes.
Maybe we should make this lock and make this lock means that the whole refill of add task is locking the task queue. Okay, right?
Okay.
If that is the case, the add task should not have this lock. But outside, when you're in your user-defined function, you should have another maybe wrapper of the add task that locks the add task. You call that wrapper. Do you understand me?
Yes.
Yeah, because we don't want the user to manipulate the queue lock, okay, themselves.
Yeah.
Okay? Yeah. And so this is the local table to queue, which means from the data array to queue. It's okay?
Yeah.
Yes, this is logic is pretty much the same as yours, right? So we move the global position forward, etc. Okay, right?
Yeah.
Yeah, and then we spawn a batch of this task. It's okay?
Yes.
Yeah. So this task spawn will call add task. So add task is protected, then it's fine. If not, we need to protect it. Okay. Maybe this is a user-defined function. User need to call add a task protect, right? So maybe some function which will call the lock and then call add task and then unlock. Okay, right?
Yes.
Yeah. So okay, so this is a pop task. In our case, it's not pop task. It's like a fetch a task and process or something, some function like that. Okay.
Yeah.
Yeah. So in previous fetch a task in the process, we just fetch a task, right? And then we down there we process. It's okay.
Yes.
Yeah. Here we cannot do that because we might need to refill, right? So previously you also have refill, right? Right. Refill and then get a task and process, right? If this is less than C, we need to refill. It's okay.
Yes.
Yeah. These things are to handle. Maybe we don't need them. Okay. We just handle the case where you really have nothing to do on your local machine, but actually there's some task waiting for other data to come. So you cannot say you are idle. That's what I mean?
Yes.
But in our case, we don't have this, so we can ignore this, right? We don't have data request. Okay. So these
Yes.
topic handling is for this field. Right. So what matters is this, right? So firstly, you will see whether you can refill from file. Okay.
Yeah.
And then if not, then you need to refill from the local table, right?
Yes.
If the local table is 4, it's another difference, right? So if 4 is, hey, the local table 4, you can nothing, right? That's fine, right? And so this thing is again from remote. Okay, you can ignore this. It's okay?
Yeah.
Right. And so this is task map, task queue. This is again, task map is where you are waiting for data. We don't have this, so we can ignore this. So basically, first it gets from file. If there's nothing in the file, then you get from queue, local queue, refill. It's okay, right?
Yes.
And then you process the task, okay? And if you finally find, hey, there's nothing here and nothing here, I don't process any task, idle, okay? Right?
Yeah.
Yeah. Okay. So basically, you need to do some fine tuning there, okay? And the condition checked by main thread, I think it should remain the same, because your thread idleness is controlling when the main thread should stop, right? Remember, we have case 1, case 2, case 3. And now the only difference is that if we add an additional requirement, right? So instead of just see, hey, whether there's anything in the queue, right? We first refill. If there's really nothing in the file and also nothing in your local data array, and there's nothing in the task, you will become idle, right?
Yes.
So when all threads become idle, they already guarantee there's nothing in the file and nothing in the data array. Okay.
Yeah.
So I think the end condition should be the same, but you can double check. Okay, you can double check.
Yes.
Right?
Yes. Yeah. Okay.
And so this is a reminder of the G-thinker, right? So we have a global queue. Right now we only have global queue. We don't have local queue, right? Okay, right.
Yes.
And what we want is this, right? So this global queue should be priority queue. So whenever you pop, you're popping one very expensive task. It's okay?
Yes.
Yeah, each time a thread requests you are getting the most expensive task. It's okay?
Okay.
Yeah. So for this reason, we need to define a function. Let's say it's a task, right? So you should define a virtual function that the system can call, okay? Right.
Yeah.
And to tell, hey, how costly this function is. This is an estimate, by the way, okay?
Estimated.
Yeah, it's an estimate of the cost, right? So it tends to be big because we don't really know how expensive it is. We rely on divide and conquer, right? So the time delay, time out mechanism to do that. Okay.
Yes.
Yeah. So here's what you can do. The default task class can just return 1. It's like everyone is equally expensive. Okay. Right.
Yes.
So user if they don't overload this, then it's like we don't have a priority. Okay.
Yeah.
But most often than not, we will give the extension S, right? Because you think about it, if now I want to extend and my 2-hop has 1 million neighbors, that's going to be way more expensive if my 2-hop has just 10 neighbors, right? Yeah. So we will return this in our actual application code. It's okay. Which Gwimu will be prepared.
Okay.
Yeah. And this will be used because it's a virtual function that the task class knows as a function like that, right? So this will be used by the system. Okay, will be the key when you pop out the priority queue. Okay.
Yes.
So the priority queue will be something max heap. It's okay. We discussed, right? It's a binary tree where the top is the most expensive one. Okay.
Yeah.
And we know that in C++, priority queue is the max heap. In the other language, it's min heap, but in C++, the priority queue is the max heap. Okay. Like in Python, PQ is min heap. It's okay.
Yes.
We covered that before. Right. So how to implement this? So you cannot just use one priority queue. You know why?
No.
Priority queue is one directional, which means this is the most expensive, right? So of course, each time you fetch, you can get most expensive. Is okay?
Yes.
But there's a problem, okay? So think about it. We also have the spill. Spill should have spilled the least expensive to disk, right?
Yes.
Yeah, keep the most expensive memory actively computing and decomposed by others. It's okay?
Yes.
So in that case, it's like you need the top to be the least expensive. This is min heap, okay?
Yes.
So we don't have both max heap and min heap. Is okay?
Yes.
Right. So what I'm thinking is that we can have a solution combining max heap with a DQ. Okay. You can also combine with min heap, right? So your choice. Okay.
Okay.
So min heap will be really picking the least expensive ones to flush to disk, right? But I think that's overdue because this is max heap, right? You need a min heap, you need to write a wrapper using the negative key, right? Something. Okay, if you don't want to do that, you can direct to DQ. It's okay, right? So here's the logic. Remember, we have CCC, right? The capacity. It's okay.
Yeah.
Right. So this thing will be the priority queue. Okay.
Yes.
So we will always, whenever we get a task, we will always get from the priority queue. It's okay?
Yes.
Yeah. And we will try to make its size always K, always C. It's okay?
Okay.
Yeah, top K, right? We have 3K capacity. It's okay?
Yeah.
And beyond the K, they will be spilled to the DQ according to the order they are inserted. It's okay?
Okay. Now K here, Professor, is like you said K is C.
K is C, yeah.
Okay.
Yeah, you can use C if you want. Okay?
Okay.
So this is always a top C task is in this. And if you have maybe C plus 3 tasks, the rest 3 will be in the DQ. It's okay?
Yeah, okay.
And the DQ, actually, the reason I prefer DQ than the others is because DQ keeps the time, okay? So the first come, first served, right? Okay? So we will not have some tasks that wait for a long time. It's okay? Right?
Yes.
Yeah, so maybe it's you don't need to use a min heap, okay? Because min heap is also complicated, right? You need to add a wrapper to max heap, okay? And is this okay? The idea is clear, right? So then you think about it. This should be a unified because our queue is protected by lock, right? We have a global queue, okay?
Yeah.
So this should be another class containing these two members, and they should act like one, okay? You don't care about the details. If you pop a task, it's always popping the most expensive task right now, okay? Right? Okay?
Yes.
And if you flush, it will always flush the least expensive ones, right? Out, okay?
Yes.
Yeah. So flush will always be safe because, you know, if you have 3C, but this must be 4, and the other C must be in the DQ, right? So that's not a problem. You can flush the rest and cut DQ here. It's okay?
Yeah.
Yeah. And pop is always safe because you can always pop from the priority queue, the most expensive, by calling the UDF cost. It's okay?
Yes.
But there's one thing that you need to guarantee. That is whenever, let's say you append, right? So you append a new task, let's say here, okay? Right.
Yeah.
What you do is, let me see how to say that. You need to first append to here, okay? Right.
Okay. And if it's not
this queue will be temporarily C+1 items. Is okay?
okay.
Oh, how to say this? Let me see. Oh, there's a problem here. so let me see. Yeah, so there's a small problem here. Let me see how to say this.
Okay.
Yeah, because originally what I'm thinking is there's always maintain top K. There's a way to maintain top K because if it's, you have a new task coming in, inserted, right? And first insert to the queue, okay?
Yeah.
But assume this is not max heap, it's min heap. Then some smallest task will pop to on, okay? Right.
Yes.
And then you can move it out into the DQ, okay? And this is still the top K most expensive task. It's okay?
Yeah.
Yeah, but this solution doesn't seem to work out right now because let me see. Because it's a max heap, right? So we cannot do that, right?
Okay.
Yeah, let me see how to do this. Maybe we need a min heap still, okay? So min heap, we actually have our own min heap structure. I can tell you later, but we can easily make a max heap min heap, right? You just negate the key, okay? And then when you get it, you negate it back. It's okay, right?
Yeah.
And then with this min heap, we will be able to get the top K. Right. Oh, I have to be temporarily gone for 5 minutes. Okay.
Okay, sure.
Hello. Hi, Jalal.
Yes, Professor, I'm here.
Hello?
Yeah, Professor, I'm here now.
Okay, good. Yeah, so we are close. So let's
Yeah, I know.
so we can have lunch. Right. So yeah.
Yes.
Okay. Yeah. So far so good, right? So you understand what we are doing here, right?
Yeah. Like the big picture I have now, I have just to maybe to read this again, go to the GitHub a little bit, just to
Yeah. So
combine
this guy
everything
cannot
together.
help you. Everyone has to digest things themselves, right? So
Yeah, sure.
Okay. Yeah. So, but you have questions, just let me know. Okay, you can ask me anytime. Okay. So
Yeah.
basically, what I'm thinking is that we can have a min heap that maintains the top k. Okay, top k items. It's okay.
Okay.
And it will keep the when you return cost, it's big, we will go to the min heap. Okay. This min heap will be the top k most expensive task right now. It's okay.
Okay.
Yeah. And whenever we add a new task, like add task, we first add to the min heap. It's okay.
Okay.
And then this min heap will become k+1 items. It's okay.
Yes.
Then we will take out the top to the DQ. It's okay.
Okay.
Do you understand what I mean? So it keeps back to the k. So this will be the k most expensive task. When we get the task, we will directly get the top of the k. Okay, it may not be the most expensive, but it's within the top k most expensive ones, right? Okay.
Okay.
Do you understand what I mean?
Yeah, but give me just a second. So like when we use the min heap, the top k one is here is the minimum one, right?
Yeah. So here's what I want to say. So you see, we have the add task, right? So we have the add task function, and sometimes we have the spill function, right? So the add task. If you look at the what's add task. A task, they have the spill from the back, you see, the QTask back.
Yes.
Right? And sometimes we have pushback, okay? Right.
Yes.
This function should be overloaded using a new data structure. It's okay?
Okay.
And in the new data structure, basically, in the buffer, how to say this? Let me see. Previously, we have a DQ of tasks, okay?
Yes.
Now what we're doing is, hey, these tasks are a big task. We should take them out into a priority queue called min queue, okay? Min heap.
Okay.
Min heap, there's a previously I want to use max heap because when we let's say we get a task, right? We get a task to process, we will get the most expensive task. It's okay?
Yes.
But unfortunately, that will cause a lot of trouble in implementing, keep maintaining the top k most expensive task. So we now revert to min heap. It's okay?
Yes.
Min heap will not be too bad because the top k most expensive task will be in the heap. Okay, so we are still getting one of the k most expensive tasks, even though not the most expensive, maybe the least expensive among the k, but it's fine. Okay, as long as we keep a k a relatively small number, right? And other tasks keep filling in here, right? And the expense task will finally pop to the top. It's okay.
Yes.
Right. Okay. So let me see how to talk about this. But maybe we don't need it so complicated. Let me see whether we let me think for a while, just one moment.
Yeah.
I think maybe we don't need this design. It's a little bit complicated. Let's see.
Okay.
So let's just do a simpler design. Okay, so let's just ignore this thing. We can still have this, I think. Let me see how to. Max heap. Yeah, we don't need this. Let's just maintain 2 queues, right? So 2 queues, okay? Just like in Gthinker, okay?
Okay.
Yeah, so let's make it simpler. So let me see. So one is a big task queue, okay? High priority.
Okay.
One is a small task queue, okay?
Yes.
And that will have low priority, okay? Right. So which means whenever we get to task, we will first always get from the big task queue, okay?
Yes.
Only one big task queue is empty, we will get from small task. Is okay?
Yes.
And each of them will have the corresponding, file list, right? So then we have 2 sets of file list. Is okay?
Yes.
Yeah. And the way to differentiate between big, small is to use this cost. Okay.
Yes.
Right. Yeah. So if the cost is larger than a certain value, larger than equal to certain value, we put to big task.
Yeah, we make
Otherwise,
it big.
we put to small task. Right. Okay.
Yes.
This will be very close to Guimu's new code. Okay, you have the URL in the paper. Okay, so you can also refer to his code a little bit. Basically, we will first lock this, right? Okay, and try to get a task,
Yeah.
right? And then we will refill this big task queue, for example. Okay, and then we will come back to small task queue. Is okay?
Yes.
In that case, actually, we can also like each component maintain small task queue. We can exactly follow the same design, right?
Yes. So yeah, each component will has two queues.
Yeah. So basically,
Big and small.
we can still use this design. Basically, let me see. I think that's pretty much the end. Yeah. So you can give me a plan. So each thread has its own queue. Okay. Right.
Yes.
And in the meanwhile, we have a big task queue. Okay. Right.
Yes.
Yeah. Shared by everyone. Okay. And big task will go to the big task queue. Small task will go to the small task queue. Okay.
Yes.
But maybe we still make them shared because in that case, small task cannot be shared among the others, right? Okay, unless you spill to disk, right? This is not desirable, right?
Yeah.
Do you understand what I mean?
The last point.
So if these tasks are in small task and the other are idle, you cannot throw them to the others. The other will be waiting. You are processing all 5 tasks. It's okay.
Yeah.
But if it's a global queue, then you don't have this concern, right?
Yes.
But it's okay. We can use a local queue because these are small tasks, right? And in the meanwhile, we can have a file list shared by them. Okay, global task queue have another file list. Okay, right?
Yes.
Yeah. So whenever spill, they will spill to the same task file list. Okay.
Yes, for each combo, you mean?
Yeah. But this again, this is a little bit complicated. We don't need. So again, still let's instead of doing this, let's maintain a big task queue, a small task queue. It's okay.
Okay.
Yeah, and they're shared. So this is a big task queue, this is small task queue, each associated with a big task file, small task file, okay, with their own capacity, right?
You mean, Professor, both queues are shared?
Yeah, both queues are shared. And you will always
Okay.
first get this task. If you get some task from here and refill, then you're done. If this is empty, then you will get this. It's okay?
Yes.
And when you refill, you will always refill big task first, right? So, right. And if this is empty, then you will refill the small. But I think the refill is relying on check this task. If this task is empty, you will always refill, right? So if still fail, you will then go to small task. Is okay? And small task you will try to refill, right? Still not, then you will refill from local object. It's okay?
Yes.
And some local object may suddenly refill to big task queue. Okay, this can happen because when you spawn, you find, hey, after spawn, the two-hop subgraph is so big, right? The cost, when you call the cost, it becomes a big task. That should be inserted big task. Okay.
Yes.
And when that happens, you should immediately stop instead of spawning C tasks to the small task queue refill. If you find ever a big task, you can stop immediately. Okay.
Yes.
Because there's a possibility that you spawn many tasks. Many of them are big, right? then that doesn't make sense, because when you have a big task, you want to stop, because this big task can be split into 1,000 big tasks. Each smaller big task can, when you see big tasks, you want it to run, decompose, and try to, you don't want to get a lot of big tasks here. So you spawn, if all small tasks, then they are attached to small. If you attach small, suddenly you find a big, you will attach a big and you stop. You don't continue to look at these. Okay.
Yes.
If there's a way to implement this in Windows code, you can take a look at how the latest gsyncer is implemented. Okay. And we can also discuss the details later. Okay. Yeah.
Okay.
Is this okay?
Yeah.
Yes, there's a lot to do, but I think you are emulating what people did before, so that's fine. Okay. Yeah, just let me know if you have any questions during the way. Okay.
Yes.
If you're implementing totally on your own, like the first time, maybe it's a little bit difficult for sure. Okay. This because you have all kinds of samples. It's more like you are catching up, right? So that will be a bit better. Okay. Just let me know if you have any questions during the implementation and like a decision making. We can make the right decision and then we implement. Okay.
Yeah, sure. Okay, Professor.
Okay, then that's pretty much it, and I will send the slide to you, and let's see again in 1 p.m. Okay. Yeah.
Okay, Professor. Okay, thank you.
You're welcome. Bye.
Okay, bye.